I'd like to thank everyone for joining us for the webinar, and I hope everyone finds it interesting and informative. What we're going to talk about this afternoon is we're going to talk a little bit about an introduction of our CombiFlash Rf Purion. It's a flash mass spectrometry system, and the key with it is it's a fully integrated system where the control of the mass spectrometer detector is all done through our PeakTrack software. All of the mass spectral data is recorded and saved in a run file, just like the UV data is. And what it really provides is it provides the ability to do mass-directed purification. Some of the topics I'd like to cover this afternoon is why would anyone want to do flash chromatography coupled with a mass spectrometer. I want to talk about how it works, give you some examples of the control and the ease of use, talk a little bit about the user interface, and then 3 or 4 examples of applications showing the utility of integrating the mass spectrometer in with the flash chromatography system. Well, first of all, let's talk about why flash mass. The obvious reason is because you can get the molecular weight of the compound that's being eluted and purified. You can get some limited structural information from the mass spectra that's generated inside the mass spectrometer. It's really what we would call the ultimate in selectivity. By that, I'm saying mean that you could selectively collect peaks based upon the target mass ion that you program into the detector. And we'll get into that a little bit later. You have the visibility of seeing co-eluting contaminants. Normally in a UV trace, if your compounds co-elute, you might see a small blip on the tail or the front of the peak. But sometimes that co-elution is buried inside the peak and it looks like a single peak from a shape perspective, but it's really 2 compounds that co-elute. By using the mass spectrometer as a detector, you can actually see the mass shift as you see that contaminant show up inside the peak. This does allow you to move to another fraction collection tube and cut out that contaminant from some of your more pure fractions. The last thing is that it gives you mass confirmation of your collected fractions on the fly. Avoids you having to do offline TLC plates or workups post-purification, and use maybe a core lab facility to do your LC mass spec assays. Just a little bit of a comparison of what you can get from a mass spectrometer versus other flash detectors. Obviously UV, the response varies by compound and the wavelength that you've selected. Not all compounds can be detected by UV. If it's a saturated compound, there's no UV chromophore that exists. And at the same time, it's not selective from the standpoint that any compound that has a conjugation of double bonds that produces a UV signal in the wavelength that you're monitoring will be seen. And so therefore you cannot separate compounds based upon the UV and do very much of identification. You can do some, but not a significant extension. ELSD is another detector that's commonly used in in flash chromatography. It, as everyone probably knows, it measures the light scattered from semi and non-volatile particles that dry in the mobile phase through the evaporation during their travel down the drift tube in the ELSD. That makes it more universal because it doesn't require any UV absorption for detection. It gives you a nonlinear response. It's still not selective because it will detect any compound that has that will form a microparticle in the drift tube in the ELSD. The mass spectrometer, on the other hand, is applicable to what we would call a broad range of organic compounds. A lot of the people that work with mass spectrometry will say that probably 70 to 80% of the organic compounds that are known to exist today will produce a mass spectrometer response. It gives chromatographic data by confirming a compound's mass. And I've got a little note there that says no advantage if only using TIC, which is total ion count. In other words, if you're summing a series of masses together, you don't get any confirming mass value. So normally you would operate the mass spectrometer in a single ion mode or a narrow range of masses, and we'll show how simple that is to do in a few minutes. Obviously, because there are compounds that do not ionize, such as hydrocarbons, it's not a universal detector. Unfortunately, there's really no good universal detector for liquid chromatography or flash chromatography today. I think the important thing during our development process was what benefits this product would bring to our customers. And during our beta testings that we sites that we performed at, these are kind of some of the benefits that they found. And first we talked about this was that you could determine the presence of a co-eluting impurity. That saves you some time because you can quickly determine that you're going to have to do additional purification needed, or that the solvent system that you selected for the purification was not appropriate, and it allows you to adjust that. You can collect over a mass range, so you can eliminate unwanted masses. Very useful in natural product research where you've done an extract of a natural product and you want to collect maybe small low molecular weight compounds, maybe in the 200 to 300 range. You want to ignore large compounds that are not of interest, or vice versa. You may want to collect compounds with ranges over 500 molecular weight. So it allows you to do that and kind of separate your compounds in a very complex matrix. At the same time, you can collect only on your target mass. If you're in a synthetic chemistry situation in your synthesis, you know what the mass of the target compound you're shooting for. You can program it so that the system only collects any peak that has that mass associated with it. Really eliminates the need for post-purification analysis. You don't have to do a TLC after the run to make sure that it is the product that you're looking for. You don't have to do post-run LCMS to verify that it is the mass that you're looking for. Doing those things really increases your throughput. If you're shooting for collecting only a target mass, you can shorten your run times because once that target compound has eluted, you can end the run and not complete the complete gradient purification run. That in turn lowers solvent consumptions and the associated costs with purchase and disposal. That all being said, let's talk a little bit about the components that make up a CombiFlash Rf Plus Purion. First of all, there's the CombiFlash Rf Plus. There's the CombiFlash Purion detection module. There's a fluid interface, and there's a roughing pump. In the photo on your screen, you can see on the left side of the mass spectrometer this box, and in this box, this is our fluid interface. What it will go into what it contains in just a few minutes, but it is really the actual heart of the system and the connection between the flash system and the mass spectrometer itself. I mentioned a roughing pump, and like almost all the LC mass specs on the market today, it requires an external roughing pump. That allows us to do a couple of things. We can pull a lower vacuum or a higher vacuum, depending upon which way you look at it. But it allows us to do not only ESI, but also APCI. The reason you need the roughing pump is, one, to get your vacuum down so that your turbo pump is protected. And the second reason for the roughing pump is because you have, doing APCI especially, you have quite a bit of nitrogen that needs to be removed during the first stage vacuum process. Just to give you an idea of the flow diagram of the fluid interface, we start off with the splitter valve, and the splitter valve is where the effluent from the RF comes into the valve and returns back to the RF. And on the other side, there is the flow that goes to the mass spec. Our system uses a single piston carrier pump, and the flow goes through, we use a prime valve to prime the carrier fluid. And I might just mention our carrier fluid that we've used is typically methanol with a slight percentage, a low percentage of formic acid, and or TFA, either one. We then go through a pulse damper so that we smooth out the pulsations of the carrier pump, through a pressure transducer, and then through the splitter valve and into the mass spec. And the function of the splitter valve is it takes a small aliquot out of the flow stream and switches it to where it's in the flow stream of the carrier pump to the mass spec to carry the sample into the mass spec for analysis. So this splitter valve during operation is constantly switching back and forth. It splits out about 1/1000th of the flow in the RF to be used in mass spectrometry detection. Some of the options that are available to on the peak track side is the ability to determine whether you want a target mass to be detected or a mass range, and we talked about that a little bit earlier. The Purion comes standard with a ESI or electrospray interface, or electrospray ionization, I should say. There is an option for APCI or atmospheric pressure chemical ionization. It's typically used for compounds where it's more difficult for the compound to be ionized. So I believe in most, probably 80% or more of the LC mass specs in use today use the electrospray ionization process. You can set the ionization to be an either positive or negative, so you can produce an M+1 or an M-1 ion, and that really depends upon your compound and its chemical structure, which one of those works best. In some of the newer HPLC mass spec systems, they automatically switch between positive and negative ionization. I just want to point out here that ours does not. It can be run either positive or negative, so you have to make that decision before you start the purification. The other thing we've added is what we call pre-purification verification. As we were developing the system, one of the things that we saw was that different carrier fluids and different additives such as formic acid and TFA produced different ions. And so sometimes you typically have your M+1 ion, but sometimes it'll add what are called addicts in the business. Sometimes it'll pick up methanol, so your molecular weight's not the M+1 that you would expect, but it's actually you have to add the molecular weight of methanol to the sample to get it to get the right molecular weight. And so what the pre-purification screen is used for is to verify that your compound ionizes and to verify what mass you should program into the detector for during the purification process. I mentioned control. I would say that our design goal was to really keep operations simple. As we talk to our customers that run our CombiFlash systems, the comment we always get is they really like how simple our software is to use. It takes a minimal amount of training, and most people can be up and running the system in 30 minutes to an hour. So mass spectrometry, when you look at it, is often perceived to be a very complex technology. If you look at if you're a true mass spectroscopist, there's all kinds of voltages, temperatures that can be set, and that varies detection. We've eliminated those. We've preset to what we feel are reasonable values, and because of that, it's a much simpler process. And I'll take you through the process of the pre-run and getting a run started. I also wanted to point out that our control, everything is done through our Peak Track software. The other component that makes up the pure ion system is our CombiFlash Rf+. This is a new product that's replacing the RF200. And it has the same flow and pressure capabilities of the RF200. It has air purge to purge the columns after the run to get rid of the liquid that's residual in the column before you dispose of the column. Just like the RF200, it has RFID sensing on both columns and the collection racks. It has solvent and waste management so that you don't run out of solvent in the middle of a run unknowingly. It'll sense that the solvents are getting low and stop the purification process until you refill the bottles. If the waste container gets full, it'll stop the system until the waste container is empty. And it also has the ability to do UV spectral displays in real time and post-run. So in addition to, when operating as a standalone, the RF+, you can view the UV spectra while the peak's eluting. In the pure ion mode, where it's combined with the mass spec, you can select and switch back and forth between monitoring the mass spectra in real time below the chromatogram that's being generated, or you can switch over and look at the UV spectra. And so you can oscillate back and forth between those two if desired. I'd say that our system is really a three-step process. The first step is to verify that the compound of interest generates a detectable ion. We talked about it's typically M+1, but it can form addicts, and so those are something you need to be aware of. Second step would be to load the sample. And the third step is to press play, set up your mass spec conditions in a startup screen that pops up, and continue from there. Now, mass spec conditions can be set up in a method and saved, and so you can eliminate the final setup. step if you know what you want to look at, but if you don't want to go into a method editor, it's not a requirement. So I mentioned step 1. This is our method development screen that you see here. Once you open this screen, it starts the carrier pump pumping, and then you simply inject a small quantity of your sample in through a manual injector that's on the front of the mass spectrometer. In about 5 or 10 seconds, you'll get your mass spec of that sample showing up here. Now what this shows is there's two colors. There's a maximum intensity and then there's a current intensity that's shown here. In this example, the green is the maximum intensity. Since this is a flowing system, the sample is flushed into the mass spec. It maximizes the mass values, and then that is pushed on out of the mass spec, and it continues to monitor the baseline. So what we did was, as soon as it reaches the maximum signal value for any mass, it locks that into the green line. And because that mass signal was so strong in this example, the current intensity, which is just baseline, doesn't show up, and it's just shows it would be a flat line down here at the bottom of the screen. So in this screen, the other thing that we can do is we can set the starting mass and ending mass. So our mass range is anything from 50 Dalton to 1200 Dalton. Typically we run 100 to 1200. If you want to look at just a smaller range, in this example we've set 100 to 500 as our range that we're looking at. The system automatically labels the 5 tallest peaks in that range with their mass ion. So you can quickly see if your target M+1 value is there. If it's not, you might look at whether it's added methanol. It can pick up sodium, is common. Some of them will bond with, form an adduct with formate. So there's some common adducts that form in the fluid path during the ionization process. So you just need to be aware of those as you're deciding what value you want to use in your collection process. Likewise, we can run this in a positive ionization mode or negative ionization mode just by choosing one of these two radio buttons. Down here, regardless of what range you set this to, that's for a display only. We always collect the entire mass spectra from 50 to 1200. You have the ability to save the data as a MS data file that you can pull up later and look at the mass spectra and review the information that you captured. And then once you're complete with this, you simply press the close button and you're done. The reason for this screen is over on the left-hand side. You want to verify that your ionization occurs and that you have the correct ionization or the correct M+1 value that you can program into your collection to use during the purification. It can be used to verify the ionization and what visible ions are there. You can use it to optimize your carrier solvent. Sometimes people switch from methanol to acetonitrile. They switch from the modifier from formic acid to trifluoroacetic acid. Rerun that on this screen and determine which is better. It gives them a better mass or a better signal. You can determine the best probe to use. You can switch on the mass spectrometer between ESI or APCI in a couple of minutes. So you can run this screen with ESI. You can put the system in standby, remove the probe, put the APCI probe in, open this screen up, back up again, and rerun it to see which one gives you the better signal or forms an ion that you are confident with. And obviously we talked about selecting between ionization and polarity. Once you've determined that, the next step is to simply load your sample, either liquid load or connect up your solid load cartridge. And the third step is to press the play button. It's located down here. Right now this was running when we captured this screen, so it's a pause. And so once you press that, then your collection begins. But just before your collection begins, this mass spec settings screen pops up to allow you to modify any of the conditions. It tells you, for example, that it's detected the probe. You can change from positive to negative ionization mode. You can choose to set the mass spec to just monitor and display the mass spectrometry signal, or you can set it to actually detect and activate the fraction collector movement based upon a threshold that's set. And this threshold is, in this case, the default is 10 times the noise level. So once the signal becomes 10 times the noise value, then it will activate the fraction collector. You can also set a range. If you don't set a range, you simply use the start mass value as your single mass that you're going to collect. And once you press OK on that screen, then the system will set up, equilibrate the column as you've set up your method, and begin the purification process. Just wanted to show you an example of a real-time display. And you can see here's your chromatogram above. Here's your choice of whether you want to display the mass spec, the UV, or neither. So you can turn it on and off at will. What it's displaying down here is, since live data has been selected here, it's displaying the mass spec at this point in time. Here's your UV signal, so you have both your UV, your mass spec signal. If you can configure the Purion to include ELSD, so you can monitor UV, ELSD, and mass spec, all three signals at the same time. And I want to point out you can monitor two wavelengths at the same time while you're monitoring ELSD and mass spec. So down below is your mass spec signal. Again, this is set to 100 to, it looks like about 300. You can format this to whatever values you want to look at. And I've just taken this area down here and blown it up so you get a better view of the mass that's going on right now. It's about a 181 is the mass of what's eluting at this point. If you've went out for coffee and you come back and the purification is running and you've missed a peak, you can simply, while you have this display, you can simply touch the screen in this position at the time you want to look at it, and it will display the mass spec at that point in time. And then it stays there until you press the live data key, and it'll go back to looking at the mass spectra at the time that's co-eluting here. So at any time during the run, you can go back and look at the mass spectra at any point, and then hit the live data key and continue back to where you're actually at in time. This is just another example of here's a peak. You might say that this is a bad peak shape. There's actually a peak here that co-elutes. And so you can see the 180, 181, which was in the previous spectra here. But now you see that at this point in time you're getting this coelution of 180, 181 and a 194, 195 peak. So if you look at the UV trace, the compound that is mixed in here does not have a UV spectra, and so it doesn't show up at 254. However, the mass spec was able to detect it and separate it into a different separate fraction. So this is probably a good time to spend just a moment on how our fraction collection advance works. While we're monitoring, in this case, the 254 and the mass spec signal, when either one of those detector signals breaks through the thresholds that have been set, then it advances the fraction collector. So at this point in time, the UV would break through and it would advance the fraction collector. And that would collect down to here. When the mass spec started seeing this peak form, that would advance the fraction collector again, even though the UV would say there's no peak there. So the two channels are totally independent of one another, and when either one sees a peak that's breaking through the threshold that's been set, it'll advance the fraction collector to the next tube. Post-run, just a quick example here. You can see that you've clicked in this position on the mass spec peak that shows up here, and it shows you the mass spec down here, and I've blown it up. And at the same point in time, if I switch over to UV, I can get my UV spectra showing at that point in time. Just like the mass spec, you can vary by clicking Format Graph, you can vary what wavelength range is being displayed in this window. And this window would show up right down here underneath the chromatogram. So you can switch back and forth between those. Obviously, you can save that as a PDF file so that you've got either UV trace or the mass spec trace at that point in time. And so you can just click in this window here, and it allows you to vary what mass spectra or UV spectra is showing up down below. So let's show you some examples here. And this is what we've got here is elution of a single compound. And unfortunately, this spectra covered this up, but it really should say collect only the desired compound while you still get the mass spectra of all the compounds. So, in other words, what we did was we monitored only at one mass range. And in this case, it was 195. And so the mass spectrometer signal started here. It started collecting in this blue vial, or this blue line. Then the UV finally started responding because it doesn't have as much of a strong a UV response, so the UV broke through the threshold, and so it switched vials and started collecting this red material. And then the UV saw a second peak, which happens to be theophylline. The mass spec did not see the second peak because we're only monitoring 195, and there's no 195 in the mass spectra of theophylline. But the UV saw this second peak coming out, and so it began collecting it as the green. And finally, once it ended, the mass spec continued to see the caffeine material, and so it went back and started collecting caffeine again. So from this, we can click on this in post-run. We can click in this area here and get the mass spectra that's displayed here. We can click in this area here, and we can actually get the mass spectra shown down here. So even though we don't see a peak for theophylline, we actually see the mass spectra at that point in time, and we can determine that it's theophylline. And here's a good example. Here's where you got a nice M+1 for caffeine. You've got a nice M+1 for theophylline, but at the same time, the theophylline formed an adduct with methanol, and that gives you the 213 peak. So in this particular example, theophylline gave 2 peaks. You can collect on either one of those 2 masses if you wanted to collect for theophylline. And this looks like it's just the same one repeated. Another example is to collect all compounds within a mass range. So what we did in this example, we collected both caffeine and theophylline because we looked at a mass range from 180 to 200. And so in this case, our mass spectra, which is difficult to see, but it's the green trace in the back, you can see where it went up for the caffeine peak, it came back down and started up again for the theophylline peak. And so we're looking at any response between 180 and 200 Dalton. And so that's what activated the mass spectra signal that you see in the background. So you could collect off the UV. We've got 2 different wavelengths we were monitoring on the UV, 254, 275. And then we've got the mass spectra signal here. And so in this case, all 3 of those wavelengths were driving the fraction collector based upon the signal and breaking through their threshold. Another example is where you might want to verify that your correct compound is collected. In this particular case, this is an example of an oxidation product that's formed, or a reaction that we've done here in Lincoln. And we were wanting our product. This was our desired compound here, 2 benzene rings with 2 amino groups, 1 on each end. This was an undesired compound. And what we found from this is when we ran this reaction, we were finding that we thought this large peak in the UV was our desired compound. Turns out it was this byproduct, which was not desired. And the small peak in the UV was actually our desired compound. But by using the mass spec for detection purposes, we're able to see that in real time, not worry about collecting this, collect these fractions here in the green, and evaporate them down and continue on with our work and ignore the other material, as well as not have to spend any time post-run re-verifying which one of these 2 peaks was our actual material. And so you can see here again, it formed an M+1 here, and it formed an M+1 plus methanol adduct here. Since we use methanol as a carrier, we see that's pretty common practice with our electrospray system. The last example I have is when you're using natural products, and you might be doing some initial screening of known compounds during the purification, where you want to concentrate your efforts on compounds that might be novel. And so this is an extract that we did of a natural product, and you see it's quite complex, and there's several different peaks that show up here. This is the mass spectra of the different collections that were detected by the mass spec. And so unfortunately this came out of a poster, but I encourage you to go online and look at we have a couple of posters that talk about mass spec, use of mass spec in detection, and this is information out of one of them, and you can actually see the fine structure of these different UV or mass spectra peaks that were collected. So a lot of times natural product chemists will know, what these compounds are because they're pretty common in plants. So what they would be looking for would be a novel peak that has a unusual molecular ion that is not a common product. So that might be what they would be isolating to look at. The last thing I just wanted to go through our CombiFlash Rf product family. We have the CombiFlash Rf 150, which is a low-cost economical product. We have the CombiFlash Rf Plus, the Lumen, the Purion. The Lumen is our built-in ELSD. We have the CombiFlash Rf Torrent for large-scale work, regular ReadySep Rf and ReadySep Rf Gold columns, 3 different fraction collectors that can be standalone units, and we have a standalone CombiFlash ELSD detector that can be interfaced with either the RF Plus or the Torrent. Last thing I wanted to encourage everyone to do would be to go onto our website, www.isco.com/flashguide. This is a 200 or 300 page book that you can order a hard copy for free. Guidelines and tactics for flash chromatography. It's got a lot of basic information. It's got a lot of information on our different solvents and UV absorbance of the solvents, miscibility of solvents. So I would encourage you to get your free copy. Again, I'd like to thank you for your time and attention. Hopefully you found some informative information today. On this slide, on the last slide, you can see that there's some other webinars coming in the future, and so we'll certainly send you notices when we have those webinars, and we hope we can see you participate in those again. So thanks very much. I hope everyone has a great afternoon.